When we last met, we discussed and derived the equation for the eccentricity vector, which I conveniently have written on the screen here. We then determined that it was a constant of motion, which was important because of two different reasons. One, that it is a constant magnitude. I probably don't have to write out the whole word, but here we go. It is a constant magnitude, which means that the shape of the orbit does not change with time. What's more, it means that it is pointing in a constant direction. Because it is pointing in a constant direction, we can use this as a compass of sorts, a landmark to point to and say, okay, with reference to this, I know where we are in the orbit. And in a geometric sense, on paper, it's going to look something like, if we know that the eccentricity points in that direction, we know that our radius points in that direction, we can measure the angle between them and know where around our host body our satellite is. Mathematically, that's going to look like taking the dot product of our eccentricity with our radius. And so let me write that down over here. Minus r dotted with r over r, scalar. So this, by now, should hold no surprises for us. We know that the dot product of a vector with itself is just the scalar of the magnitude of that vector squared. This is an interesting quantity right here. This allows us to explore something called a scalar triple product. And in the interest of time, I'm not going to spend too much time going into detail on this, but the short version of this is that we can rearrange this to be a little easier to work with. But before I write that down, let's take care of the left-hand side first. So whenever you have a vector dotted with another vector, that is going to be the magnitude of both of them, so in scalar form, eccentricity, then radius, and then you're going to take the cosine of the angle between them. This is the angle that we pointed to here. And that's what that looks like. Mu. And rearranging this, we can show we have r cross r dot dotted with h minus r squared over r. And I'll go ahead and I'll start with this one because I'm already here. We can reduce that down to just become minus r. We have already dealt with that quantity before. That is h. Didn't have to get rid of it. That is h, which h dotted with h, we know what to do with that, don't we? So we have er cosine of theta is equal to magnitude of h squared over mu minus r. And these are all scalars now because we've taken dot products. All right, so we have a radius over here and a radius over here. Let's get them all on the same side. We have r plus re cosine theta squared over mu. Well, we can actually take the radii, the radius, out of that left-hand side equation there. And then we solve specifically for radius. That is our radius equation with respect to theta, where theta is our true anomaly angle. And that is just the name of that angle that we have decided to give it. All right, that's pretty easy, wouldn't you say? Let's do an example just so that we can flex our new muscle. And so let's say we want to find what the radius of the system that we've been looking at this whole series. So where our specific angular momentum was, let's see, that was 87,481 kilometers squared per second. We know what our mu is, where it is 3.986 times 10 to the fifth. Whoa. All right, kilometers cubed per second squared. Not whatever I was trying to write down before. Our eccentricity is going to be not 0.2, which we derived from our previous episode. Let me double check. Scrolly. There we go. Not 0.2. And let's find it. Let's find out what our radius is at an angle of, let's do 30 degrees. All right. We'll start with the numerator. We have h squared by mu. That is going to be 87,481 squared. That is going to work out to be kilometers to the fourth by second squared over 3.635 kilometers cubed by second squared. And these will cancel out to create kilometers. Where, oh dear. We have our numerator being $19,199.5169 kilometers. Underline that so we don't lose it. And then our denominator is going to be, tell you what, I'm going to scroll down a little bit. I'm going to write it down here. So we have R equals 1 plus 0.2 times the cosine of our true anomaly angle, which is not 20, but 30. 16,365.01 kilometers. Well, wouldn't you know it, that's the radius that we've been playing around with this whole series. It's almost as if I did this intentionally. All right. Let's see. Scroll down. I'll scroll down a little bit. Get some new space to work with. So there are two quantities that maybe we are curious about knowing. Like, for example, what is our radius when our theta is 0 degrees? What radius do we have when we are perfectly aligned with the eccentricity vector? So plugging that into our cosine here, cosine of 0 degrees, well, that's going to be +1. That means that our radius equation turns into squared by mu over 1 plus the eccentricity. And if cosine is 1, that is the largest that cosine is ever going to be, which means that this is the largest that this denominator is ever going to be, and our numerator is a constant, which means that this is the smallest radius that we are ever going to see. And we will call that periapsis. We will denote that as RP. Box that in for us. All right, well, if being perfectly aligned with the eccentricity vector gives us a special value, an important value, then one might assume that if we are at the opposite direction from our eccentricity vector, we should have an equally interesting value. And sure enough, if we plug that into our cosine here, that is going to be -1. That's the smallest that cosine is ever going to be. So if we rewrite our equation here, if that's the smallest that our denominator is ever going to be, then that's the furthest away that our satellite is ever going to get. We will call that the Apoapsis. And then depending on, mark that as R sub A, depending on where you are, what body you're orbiting around. If you're orbiting around the sun, sometimes you'll give it a fancy name like the aposole or the parasol or the perigee if you're orbiting around the Earth, apogee. Just know that these are both referring to the periapsis and the apoapsis for those bodies. So, I don't know about you, but I'm curious enough. What is the periapsis and apoapsis of our Earth satellite system? Glad you asked. We know that this is a constant, so I will go ahead and not have to derive that again. That is 19,199.51169. Does that have all the digits? That's all the digits. Over 1 plus 0.2, which then becomes, if I round it to the nearest kilometers, 16,000 kilometers. It's very handy. And for our Apoapsis, when we plug that in, again, rounding to the nearest kilometer, that turns into 24,000 kilometers. And it may be a short video, but already we've derived the equations for radius at any point in our orbit and the minimum and maximum points for distance, or the minimum and maximum distance in our orbit. And I think that's about as good a place to stop as any. So without further ado, I'm going to go ahead and stop it there, and we'll pick it up in the next episode. Thanks for stopping by.